meeting by about a half an hour from our typical time, and we do that because we hope to have a good discussion. I'll keep some time here so we don't run, like into the cocktail hour. And we'll start with Patrick Heimbach, who will give us an introduction to the subject for about 5 minutes.
Yeah, thank you. Let me share my screen. I need to be made host, I think.
You should be able to now share your screen.
Okay, well, thanks everyone. It's exciting to be talking about and providing a perspective on how we look at observing systems through the lens of models, the overarching topic. And I'd like to give a very quick overview and flavor of the rich set of quantitative methods that formalize and support the design of effective observing systems. And just right away, sort of a take-home message is that ultimately, and through iteration, we learn jointly about the data, the observations, the model, the uncertainties, the system that we're studying, and then the target quantities of interest. And whenever I say target quantities of interest, what I might mean, for example, forecast error, forecast skill, or climate indices such as AMOC strength, content in other contexts. So let's, there was my first slide already here that I forgot to put forward. But so let's start with highlighting the first big difference between observing system simulation experiments versus observing system experiments. Observing system simulation experiments, when we deal with those, what we do is we generate hypothetical observations from high quality simulations usually, and those are called nature runs. And these simulated observations are then used in a data assimilation framework to evaluate how they impact our target quantity of interest. So again, that could be forecast skill, forecast error, climate indices. And later, Cecilia Bitz will talk about an application in the context of sea ice prediction. Then the variation thereof. So we had this year, that's the observing system simulation experiments. Variation thereof is when you see this one box sort of changing between data assimilation and forward model. So we might call those OSSI type methods. So they're still observing system simulation of experiments, but you do not include a data assimilation scheme. Usually we just use the forward model to help out with how these simulated observations may inform our quantities of interest. And Nguyen today will talk about sort of exploring how Arctic Argo floats may provide us information of Arctic hydrography. So different to that are observing system experiments. And so now the simulation has dropped, so we no longer have OSSE, but just OSEs. These are also sometimes called observation denial or observation withholding experiments. And here we are looking at the impact of adding or withholding real observations within a data assimilation framework. So you notice the role of nature run has disappeared, and compared to the one before, the simulated observations is now replaced by real observations. Next, in line, we have a set of approaches that are generally called targeted observations. That's a broad theme, and that generally involve adjoint and tangent linear models. And there are several flavors of these approaches. One that provides a comprehensive assessment of the sensitivity to observations, and in the meteorological community, in the numerical weather community, oftentimes that's referred to as forecast sensitivity observation impacts, or FSOI, and there's some examples here. Next, there is one where we are assessing the maximum transient growth of our target quantity of interest. That could again be forecast error, or it could be the AMOC strength growth over a finite time interval. And those are usually targeted via singular vectors. And then finally, we have one where we're quantifying the uncertainty reduction that comes about through the use of certain observations within data assimilation framework. And now here we're looking at Hessian singular vectors. So the Hessian refers to a second derivative as kind of a curvature. It's how certain observations sort of help to constrain or not constrain our data assimilation scheme. And again, today, we'll hear about this subject from Nora Loose later today. And so, yeah, so that's so much here, I think, remains to be done and to be explored and to be learned also from the numerical weather prediction community, where some of these methods have been very well developed and are actually regularly employed. And so with that, I hope I've maximized your curiosity and hand it over to our next speakers. Thank you.
Not only did you maximize exactly 5 minutes, so that's actually remarkable. Thanks, Greg. I think we'll hold questions until the end, so we get the whole package. So the next presentation would be by Cecilia Bitz, integrating sea ice modeling and observing system design.
Great. Start. Is it correct?
Yeah, that looks good.
Great, thanks. Well, it's a real pleasure to talk to you today, and I'll just get started quickly. I'm going to talk about an application of observing system design with sea ice modeling. And I want to start with my motivation, which is prediction. I'm really interested in seasonal, short-term, couple weeks out to maybe a year or two prediction in the Arctic, as well as long-term prediction, like trends in the Arctic. And this is a picture showing our best models today. These are all operational models that are predicting sea ice out to, you can see 10 weeks or so here. And the prediction here is of the sea ice concentration, which we then convert into an extent, and then look at the comparison by grid cell. So this is a particularly detailed look with observations. So these are retrospectively looking back. And that's a squared error metric, so lower is better. And the black line, the solid black line, is a climatological estimate, so purely observational. What this shows is that we actually see very few models actually better than a purely observational estimate. Incidentally, all of those models that are below the line are actually from the ECMWF group. So why aren't forecasts doing better? Well, I think primarily it's poor initialization and model bias. Well, what can we do about that? Well, we could do better data assimilation with more variables. So most of these models only assimilate sea ice concentration, only 1 or 2 assimilate anything beyond that, and that would be a little bit of thickness data. We need better observations, and we could do really optimize the observations used with targeting which observations we need. We could improve our models, and we could also bias correct. And I'm going to show an example of bias correction because it really illustrates the problem with model bias, both in the initialization and the evolution of the model. So this is just the ECMWF model, and I've changed the x-axis to lead time in months now, so we can really look at a longer period. And that's not my dog. Anyway, what it shows is here, without any bias correction, the model only is better than the observations for about less than a month. But we can actually bias correct just with purely statistical methods alone by evaluating where the model disagrees with observations in a systematic way. And with that, we can actually beat the climatological benchmark estimate of skill for 2.5 months, which is really outstanding. So we have a huge opportunity to do better, and we can do it with data assimilation and more observations integrated into our models. So this is just an illustration of a data assimilation method. I use Ensemble Kalman filter, where the model sits outside of the framework for data assimilation. Let me rephrase it. It's not they're not joint models, they're separate models, so they are kind of successive, and that's considered a non-intrusive method. The idea is that you bring your observations and your model together, and you do some statistical analysis to see how you want to adjust your model and then you do so, and then run the model a little bit more. So these are observing system experiments that are asking the question with just purely hypothetical observations. So we extract the observations from a simulation itself. It's kind of like a nature run, except because it's ensemble Kalman filter, we have a whole ensemble. So we just choose one of those ensemble members without any data assimilation to be the truth. And then we compare, first of all, in this figure on the left with the ensemble mean. And it's by design, it has error. Now we want to fix that error with data assimilation. So if we just assimilate sea ice concentration and then compare it to the metric of concentration. So we're assimilating concentration and seeing how much better we do with concentration. It does a lot better. But that's kind of no doubt, right? Because we assimilated concentration and then compared it to concentration. But what if we actually assimilate thickness instead? That's a different variable than the one we're evaluating against. And it's even better. So that's pretty amazing. And that's because this is a multivariate method. So you can take advantage of the fact that these variables are correlated and assimilate one variable, constrain the model with one variable, and improve another. It turns out this last column shows that a very different variable, the age of ice, whether it's first year or multi-year, as another hypothetical variable that we're assimilating, is also a very good way to constrain the model. And then how does this affect the thickness? So here we really show how much we shine when we assimilate really more variables than just sea ice concentration. Well, sea ice concentration doesn't improve the thickness in the model much at all, but it does, obviously, assimilating thickness improves thickness, and assimilating age does a pretty good job. So age we might be able to get from observations with satellites that can measure the sea ice roughness. So one last just demonstration of a model result is now to ask, well, those previous, the previous slide, those were assimilating full fields. So it was as if we had observations everywhere in our grid, which is great, but it's not always the case, right? Sometimes we only have observations at some particular location, or from a flight track, or from a satellite track. And here we did another hypothetical experiment, but here we only assimilated thickness along hypothetical ISAT-2 tracks. And I think there are about 12 a day. And over a month, then we would be assimilating 12 times 30 different tracks across the Arctic. And you can see that even though it's limited in area, because assimilating at one point can influence the region around it strongly, this is a very successful reduction in the error. So when we see the error reduced, that's a sign that the data assimilation is doing its job. So with that, I just want to end with a couple of comments about where I think we could go forward. And just to say, first of all, I use Ensemble Kalman filter. It's different from what Patrick Heimbach's group does, and his group members will tell you a little bit more about some of the great things that they can do. But what this method excels at is, well, it is multivariate, both methods are. The biggest news is that it's fairly easy to add a new observation. That's key, right? When we can act fast, when new observations become available, we can grab them and use them. It's also possible, because the model lives separately from the data assimilation method and infrastructure, it's really easy to improve the model too. So we can take advantage of new improvements in more model physics, changing the resolution at a particular spot to really improve simulation, say in coastal regions. All that can be done quickly. You know, the dynamic model can actually be very sophisticated. And we can even use this method to tune parameters. So we can constrain the model physics with observations, which is pretty cool. And then, of course, it's not ideal for other things. One of them being it's not an inverse method. So we can't ask at one time, where's the best place to make observations? But what we can do is say, well, what if we put an observation here? How does it improve our results? And then finally, what kind of practical examples are there of how models can inform observing systems out there? And I've made some cases here for that. It's really good for testing hypothetical locations for observations and how they can in fact influence reanalysis, which is what I was showing results from. So what you then would take as an initial condition and go forward into a future prediction. And I haven't shown you whether it improves the future prediction, but I think we can assume that if we have better initializations, we're likely to get a better prediction. And it's just not a step I have had the time to take yet. Other things we might expect out of this is to have these observations tell us maybe where's the most important place to put our observation, this method could tell us where the most important places to take observations for particular questions, like if you want to know more about how Arctic cyclones play out, how interannual variability is influenced by observations, and long-term trends. We can also produce daily maps. So if our observations are pretty limited, like for example, for the ISAT-2 data, we can still produce daily maps when we assimilate those data into a model. Where, in fact, if we just took the satellite data alone, we'd be very reluctant to make a map because you would have to interpolate it tremendously to get a daily picture. So instead, they're usually providing monthly. And I'll just end with saying that there's other kind of related methods, which is to use these methods to test algorithms in satellites and ways we translate measurements to observations. Thank you very much for listening.
Thanks. That was great. And I apologize. Neither my dog nor I were muted, so that's my fault. Again, we'll take questions at the end. I'd like to move on to the next one then, which is ASI for Arctic Argos. I'm particularly interested in this one because I believe this is by Nguyen. I believe this was a proposal that I recommended for funding, and so it's always nice to see things come full circle. So with that, take it away, Ann. I think you're muted, Ann.
Yeah, can you see? Hang on. I think I need to do the swap. Yes?
No, it was better before.
Yes.
Yep, perfect.
Okay, great. So start my timer. Yes, I would like to provide an OSI type example of assessing the impact of synthetic Arctic Argo type float measurement in a state estimation framework. And as Will mentioned, it was funded by NSF, and we now have a manuscript in revision on this. Yeah, so before we talk about new observation, generally we would like to understand or assess what the best information we can extract already from the existing observations. And typically in our group, we do that by performing a data constraint and dynamically consistent adjoint-based inversion at decadal timescale. And so that's what we have been doing, I have been doing for the Arctic. And one of the things we notice is that even though we incorporate all of the observations in, we still have persistent bias in temperature and salinity in many places in the Arctic. And that partially is due to the fact that we have unconstrained observation in the oceans. And on top of it, also unconstrained model parameters. And I give an example here of what I mean by some unconstrained other properties map into bias in temperature salinity. This is a map of a schematic map of the ocean circulation at 300 meters for just the Atlantic water inflow from our understanding, Atlantic water flow. So our understanding is that there's a rim current that the Atlantic water flows around the boundary and eventually exits through Fram Strait. If we overlay it with the map of, for example, all the existing hydrography, or in this case, the ITP data, the one thing we notice is that most of the observations are actually in the interior of the Arctic. And so you can see along the path of the important water mass, there's a large unsampled space. And as a result, we ended up, and not knowing the velocity here, as you can see, we will have likely a large bias in the properties of the water incoming. So we would like to understand what kind of additional observations that can complement ITP, for example. And when we think of ocean circulation, we naturally think of Argo floats because we know that by design they are to drift with the ocean current. And on top of that, Argo, there's also a very well-established infrastructure. It's low cost and easy to deploy. It has standardized procedure for data quality management and distribution, and it has international support. Relevant for the Arctic, we also know that there's a decline in sea ice cover. So in this case, this is a map of open water fraction as a function of time. So you can see there's a trend increasing. And that's important because we understand from Argo deployment that generally it drifts with the current, and then at some period it takes a profile. When there's no sea ice, like in the lower latitude, then you would it would surface and communicate its position and the information to the GPS. But when there's sea ice, then actually it cannot surface, and as a result it would go down again and continue to drift. So it continues to collect the data, but actually more and more we don't know where it had gone. And so we begin to accumulate error in the positioning, and that error will clearly maps into the measurement of the temperature and salinity because we don't know where the positions are. And so we perform a OSCE type experiment to try to quantify that kind of growth of error and whether the measurements can be useful for our purpose of constraining the state estimate. So for the nature run, our understanding of the nature run is that it should be a representative of the true ocean. And for that, we use the Arctic subpolار state estimate, which is a adjoint-based state estimate that takes into account all of the available data we have at decadal time scale. And we know that it strictly obeys the model physics, and therefore we can understand flows and budgets, etc. And so from this nature run, we generate two sets of data. One is an approximate flow field, which is captured by the mean flow plus the eddy variability. And the reason we generate a approximate flow field because we think we trust this more, the mean and the variability rather than the true three-dimensional flow that I had mentioned before, that we don't have good constraint for velocity in the ocean. And in addition, we also generate fully 3D TNS from which we will sample from. And so the various simulations will then run by which we first seed the floats in the Arctic, and then we advext it with the flow field. And then wherever it goes, if there's sea ice, then we understand it cannot surface, and therefore we begin to accumulate the temperature, salinity, and the position, so we can begin to accumulate the error associated with when it cannot surface. So the experiment looks like this, where we seed the Arctic thoroughly with floats, and that's because we want to understand statistics of the error, and that's why you put a lot of floats in. And for each of the float, we have 200 simulation. So this is an example of one of the true, or from the nature run, the true trajectory of one float over the lifetime of Argo. And where you see the ovals, that's where it can surface. So for example, this section A to B here, you only surface here and there, and everywhere in between is when we don't know where the position might be. Yeah. So that's shown here in green, the true trajectory. And then these are the simulated based on the advective. And so you can see the position can start growing in unknown, with unknown errors. And so from there, you in fact have 200 backward trajectories, 200 forward trajectories. So for every single float, you actually generate a lot of statistics of errors you can compute. And the errors are quantified as follows, where the temperature salinity from the trajectories, subtract the true trajectory temperature salinity, weighted by the uncertainty related to the temperature salinity in the model. So it's a combined model data error. Yeah. And when that error is less than or equal to 1, then we quantify that as useful for constraining the state estimate. So when it's larger than 1, then the information is less useful. But I should emphasize that it can still be very useful if there's no data wherever the float has gone, because when you don't have data, then any measurement, even within plus minus 2 or 3 standard deviation, can be useful. So on the results, the first result that we can generate is not yet on the error, but on the frequency, how often the float can surface. So because we know where the CIs are in the synthetic run, and so you can actually calculate that statistic. So this is a map of the frequency, how often the float can generate, surface in the Arctic. And I also overlay on it the contour for the minimum sea ice extent, the decadal minimum sea ice extent. So you actually can see that in the seasonal ice zone, it can surface quite often, you know, somewhere between 1 day to 8 months, how often it can surface and communicate the information. But in the multi-year ice sector, then it can take up to 2 years or so before a float can finally surface. So then you can see the error can really accumulate during that time. So we want to understand that error. And the error is also not only a spatial pattern, but also a function of depth. Because in the upper ocean, it is more directly influenced by the atmospheric control. And as a result, the variability can be very high. So when the position grow in error, then the error in temperature salinity can grow. So we find that most of the Arctic, except for some selective locations, the error can be too large for it to be useful. And this again is the useful measure of above or below 1 standard deviation. But we find that if you go down 100 to 300, then already the information can be useful, and more particularly if you go in the deep Arctic where the variability is less. So you can actually accumulate large error in position, and yet actually the uncertainty in the hydrography is small enough for the information to still be very useful for the Arctic over the entire basins, and in particular along positions where it can be very complementary to Argo flows sampling at the moment. So then can really constrain where we don't yet have the information. So in summary, knowing that the Arctic sea ice is declining, we explore the possibility for deploying Arctic Argo type floats. But we understand that due to the presence of seasonal and multi-year ice, that the floats can have problem reporting its position, and as a result will accumulate error. So we need to understand or quantify that error before we start deployment. And from our experiment, the key information we can gain from here is that the Arctic Argo type float measurements can be very useful for constraining our state estimate pretty much over the entire Arctic basin under 300 meters and even higher as well in the water column. But I want to emphasize here that we need to understand this is an iterative process, and iterative in the sense that we know the nature run. There can be a discrepancy compared to reality. And so what we need to do is sort of understand this recommendation or assessment, but then we have to deploy and obtain new data to reconstrain the model. And then through that process, eventually you would end up with the real improvement in the model. Thank you.
Thank you, An. That was really great. That was very clear. I've got a couple of questions, but we're gonna save those for the end. Next, we're gonna do an OSSI application for the Barents Sea ice prediction from Mitch Bushuk. So you can share your screen.
Okay, can you see my screen? Beautiful, okay. Yeah, so thanks to Patrick for doing a nice job introducing observing system experiments, or OSEs, and I'm gonna highlight one such example targeting sea ice predictions in the Barents Sea in this work. Just like to thank my co-authors from GFDL who are listed here. Okay, so the topic of this talk is gonna be the question of, can we predict the winter sea ice edge in the Barents Sea? So just a quick introduction to the Barents Sea oceanography. It's a shelf sea located just north of Norway and Russia. And it's characterized by a largely unidirectional inflow of relatively warm and salty Atlantic water. And then in the northern part of the Barents Sea, it runs into this mass of relatively cold and fresh polar water where it forms this polar front. And the position of this polar front largely sets the position of the wintertime sea ice edge. On the right, I'm looking at the observed time series of winter sea ice extent. And so you can see that there's this clear downward trend over the satellite era. But in addition to the trend, there's also this really rich interannual variability that we see in Barents sea ice. And so a natural question you can ask is it possible to predict these interannual variations that we see in the winter sea ice edge? So the emerging answer to that question appears to be yes. There's been a number of recent studies that have showed that the Barents sea ice extent is predictable in winter at lead times of 5 to 9 months. And these studies have attributed this skill to different combinations of persistence of subsurface ocean heat content anomalies, ocean heat transport through the Barents Sea opening, and also persistence of sea ice area anomalies. So in this talk, I'm going to be focusing in on predictions we made with the GFDL dynamical seasonal prediction system. This is based on a relatively old dynamical model, GFDL CM 2.1. It's a fully coupled model with relatively coarse resolutions of 2 degrees in the atmosphere and land components, 1 degree in the ocean and sea ice components. And we initialized this model using GFDL's in-house weakly coupled data assimilation system. So this is based on an Ensemble Kalman filter approach. And we're assimilating atmospheric temperature data in the from NCEP2 reanalysis data, satellite sea surface temperatures, and then a whole variety of different ocean temperature and salinity profiles from Argo, CTDs, XBTs, and a bunch of other sources in the World Ocean Database. And as I mentioned, this is a weakly coupled data assimilation, meaning that we compute our covariance updates within a given model component exclusively. But then the forecast step of the Ensemble Kalman filter is done using the full coupled model. So those updates are shared via fluxes between the various components. And in that sense, the ocean and atmosphere assimilation can impact the sea ice. Okay, and then using this system, we ran a whole suite of retrospective seasonal forecast experiments spanning the time span 1981 to 2016. And these are forecasts initialized on the first of each month and then run for 1 year of time as a 10-member ensemble. Okay, so just as a quick look, here's the performance of the system for predicting that time series of Barents sea ice extent. The black curve is the observed time series, and then the blue curves show various predictions of that at different lead times, ranging from 0 to 11 months in advance. And I think you can see by eye that the system does appear to be capturing at least some of these interannual fluctuations in sea ice in the Barents Sea. One other thing that really pops out to your eye is the predictions look quite bad, frankly, in the last 7 or 8 years. And we've consistently been over-predicting the sea ice extent since around 2009. I spent some time looking into this and eventually traced this back to a change in our observational data stream that happened in 2009. And what that change meant was that CTD observations were no longer making it into our assimilation system. And the Barents Sea, as many of you know, has a lot of CTD observations, as you can see here. This is the 2010 coverage in this map. So our initial hypothesis for this work and motivation was just the very simple question: if we added the CTD data back in to our assimilation, could we improve the predictions in this recent record here? And to get at this a bit more systematically, we ran a whole hierarchy of these observing system experiments. So these are a number of different data assimilation runs, starting with a control experiment where we assimilate all data types, and then a no CTD run where we exclude CTD data, a no subsurface run where we exclude all subsurface ocean data, an SST only run, an atmosphere only run, and then finally an uninitialized run where we don't assimilate any data, but we do still use historical radiative forcing estimates to force the model. And then after doing these data assimilation runs, we can then run retrospective predictions from each of these 6 assimilation experiments. And we do that initialized on Jan 1, April 1, July 1, and October 1. And this lets us assess the direct prediction skill impact of all these various observation types. Okay, so a first thing we can look at is the representation of sea ice extent in these different assimilation experiments. So the black curve here shows the observed seasonal cycle of Barents sea ice extent, and the dashed gray line shows the uninitialized experiment. So you can see that the free running model has a very notable positive bias in essentially all months of the year. Now, if we add in the atmospheric data, you can see that we get a slight improvement in that positive bias, but still retain a notable positive bias. If we assimilate only SST, we get a larger improvement. If we assimilate SST and atmosphere, it looks pretty similar to SST. And then if we add in the other subsurface ocean data besides CTDs, we get another small improvement. And then finally, if we go ahead and add in the CTD data, you can see that we get a reasonably good match with the observed seasonal cycle of sea ice extent. Now, of course, to make a prediction, you need more than just a good climatology. You need to also capture the interannual variability of the fields that, that determine the predictability of that system. And so, as I mentioned earlier, earlier work has shown that the subsurface heat content is really the key source of predictability in this region. And so here I'm showing the observed time series of Barents subsurface heat content in black. The gray line shows the uninitialized run, which you can see has a notable cold bias. It also doesn't capture the interannual variability, and it has a trend which is too weak. Okay, so now if we look at the runs that only assimilate surface data, you can see that those runs have somewhat improved the cold bias, but still have a cold bias relative to OBS. But interestingly, these runs do appear to be capturing some of the interannual fluctuations in subsurface heat content. And so this was kind of an interesting result, that with surface data assimilation alone, we could capture the subsurface temperature variability with some fidelity. Now, if we add in the other subsurface ocean data, besides CTDs, it looks fairly similar to the surface-only runs. And then finally, if we go ahead and add the CTDs in, we get a fairly nice match with the observed time series, both in terms of the climatology, the trend, and also the interannual variability. Okay, so we've shown that we're able to improve both the ocean and sea ice initial conditions via these various data types. And then the next question is, can we do these improved initial conditions actually lead to improved sea ice predictions? So to get at that, we ran a series of retrospective forecasts, as I mentioned earlier. And here I'm just showing a few case studies. These are lead 8-month predictions. These are July 1 initialized forecasts of the following March sea ice edge. And the black curves show the observed sea ice edge, and the blue line is the prediction that includes the CTD data. And at least in these 4 years I'm showing you here, I think you can appreciate that the CTD seems to be the very clear winner out of all these experiments. We can look at this more carefully by looking at some prediction skill metrics. So here I'm plotting normalized root mean square error values for different target months, ranging from January through to June. And by normalized, I mean that the RMSEs have been normalized by the observed standard deviation. So basically lower NRMSE equals higher skill. And you can see that there's this, this very nice monotonic reduction in RMS errors as we add additional data sources into the assimilation. So there's clear value to these various observation types. And the most striking value comes from the CTD data in these plots. And you can see that by just comparing the blue curve to the green curve. Shows you the direct impact of just assimilating the CTD observations. And the RMS errors decreased by somewhere on the order of 50% just from the CTD data alone. Now, of course, some of this improvement I'm highlighting here is coming from just the improvement in climatology. So we can also look at the anomaly correlation coefficient, or ACC, which is insensitive to the mean bias. And the ACC plots show a somewhat different story in the sense that the blue and green curves tend to be relatively coincident with each other in these plots, and they're systematically higher than the runs that only assimilate surface data. And so this is suggesting that you need subsurface ocean data besides CTDs in order to capture strong anomaly correlations, specifically data coming mostly from Argo and XBT in this region. One key point here, though, is that these ACCs are computed including the trend, which is a large contributor to the variability over this time series, over this time period. So we can also look at a detrended ACC metric, where we've linearly detrended both the predicted and observed time series. And interestingly, if you were to, it's very hard to pick a winner in this plot. Generally, the red line, the atmosphere-only run, has the lowest skill. But what we find is that any run that assimilates sea surface temperatures has a similar detrended anomaly correlation coefficient. So kind of putting this all together, the fact that SST is able to get you the same detrended ACC suggests that it's really the SST data that's providing the key source of interannual variability in this region. The RMSE showed us that the CTDs are primarily improving the climatology. And then the ACC, including the trend, suggested that it's the other subsurface data that's providing improved predictions of the trends in this region. So it's kind of an interesting message that there's quantifiable value to these various observation types, and the value you prescribe to a given observation is quite dependent on the prediction skill metric that you choose to use for your problem. Great, so that's all I had to say. So just to quickly wrap up, we've shown that assimilation of both surface and subsurface ocean observations can improve dynamical seasonal predictions of Barents sea ice. And we found that the most significant prediction skill improvements are associated with CTD and SST data. And we found that subsurface ocean data primarily improves the representation of climatology and trends, whereas SST provides the key source of interannual variability. And these results highlight the crucial need to sustain existing in situ CTD and satellite SST observing networks. And a point that I didn't really have time to get to in this talk is that I think these OSEs can also provide very critical insight into the physical mechanisms that actually underpin predictability. So in that sense, it's not just about telling us which observations are most useful to get skillful predictions, but it's actually telling us about the fundamental physics of the problem and contributing just to basic understanding. And I just like to finish by saying that I really strongly advocate using this approach for other observation types in the Arctic and also for summer sea ice prediction applications. So thanks a lot for your attention, and happy to take questions, I guess, in the discussion period later.
Thanks, Mitch. Yes, we'll do the questions at the end. We've got one more. That was really interesting. Having spent a lot of time in the Barents Sea, that was great. We've got one more presentation by Nora Loose, an example of optimal experimental design.
Yeah, thanks, Will. I'll share my screen here. You can all see my screen. Yeah, cool. Okay, yeah, the title changed a little bit. So in this final talk of the webinar, I want to talk about a method that is called targeted observations via uncertainty quantification. And my intention is to really leave out all the math and technical details here and rather explain the dynamical concept that is at the heart of this method. Oh, right. So targeted observing system design seeks to place instruments with a specific target or goal in mind. And this goal is often centered around one or several quantities of interest. So let's assume that we're interested in quantifying and observing the changes in subsurface heat content of the Arctic Ocean. And the objective now is to design an observing system that best informs our quantity of interest, given the logistical and technical challenges that we are facing in the Arctic, and also given the already existing observational network. And to do this, we can and should exploit that the ocean is connected over long distances and timescales. For example, the Arctic Ocean is connected with the North Atlantic, partly via these near-surface currents that I'm showing in this map. And ocean connectivity implies that Arctic Ocean heat content may co-vary to some extent with better observed quantities elsewhere, potentially with the recently deployed OSNAP observations in the subpolar North Atlantic. And the conventional approach to assess covariability is to use statistical correlations. So if you were to follow the statistical approach, you would try to find an observable quantity which shows high correlation with your quantity of interest. But the problem with statistical correlation is that we cannot always be sure that they are based on dynamical relationships and causation. So here we're actually looking at one of my favorite examples of a spurious correlation. The per capita cheese consumption in the US correlates with the number of people who die by becoming tangled in their bed sheets. So statistical correlations, they don't guarantee causation. And even if there was a causal relationship between cheese consumption and bedsheet tanglings, statistical correlations don't give us the causal driver. So what we do here, in contrast to statistical correlations, we want to assess dynamics-based covariability using an adjoint model. And I'll explain what I mean by this on the following slide. So let's assume there is a a positive northward wind anomaly in this green box west of Iceland, you can derive from basic ocean dynamical principles that this wind anomaly induces a pressure anomaly along the Icelandic coastline, and the resulting pressure gradient spins up an anomalous barotropic circulation around Iceland, which is clockwise. And this anomalous circulation pattern weakens the cold East Greenland current, and at the same time also weakens the warm Atlantic Norwegian current. So what I'm showing you next is a model perturbation experiment where I'm applying exactly such a northward wind anomaly in this green box. And here we're looking at the temperature response at about 500 meters depth. And yeah, we're seeing temperature anomalies, basically as predicted by the mechanism that I've just shown you. We see a warm temperature anomaly propagating toward the Labrador Sea because of a weakened cold East Greenland current. And at the same time, there is a cold temperature anomaly propagating into Nordic seas because of a weakened warm Norwegian Atlantic current. And this cold anomaly eventually also propagates into the Arctic Ocean. So the end result here is a positive anomaly in heat transport across Osnabrück West, a negative anomaly in heat transport across Osnabrück East, and a negative anomaly in Arctic Ocean heat content. And I call this a dynamic space covariation between the three quantities, because we know where this covariation originates, namely west of Iceland. And we also know the underlying physical mechanism. So wind west of Iceland is one example for driving dynamic space covariation. But how can we identify all of such drivers? And this is where the adjoint model comes into play. So here we're looking at three maps, and these show the sensitivity of heat transport across Osnabrück West, heat transport across Osnabrück East, and Arctic Ocean heat content to meridional wind stress, computed with the adjoint model. And we notice that all three quantities are sensitive to wind west of Iceland, as they should be, right? After what we've seen on the previous slide. So now we are ready to quantify the degree of dynamic space covariation between OSNAP and Arctic Ocean heat content, namely by comparing such sensitivity maps. And a pattern correlation of those two wind sensitivity maps gives us a value of about 0.4. And the closer this value is to plus or minus 1, the higher is the degree of dynamic space covariation, and the higher is the degree of OSNAP East heat transport to inform our quantity of interest. And we see that the scale of OSNAP East heat transport is mainly due to largely matching sensitivity patterns in the Nordic seas here. And we also see that OSNAP East heat transport is not sensitive to wind anomalies in the Barents Sea and in Fram Strait regions, which are in turn important for changing Arctic Ocean heat content. So this is why this value, this blue bar, is not higher than 0.37. And if we do the same pattern correlation for Osnabrück West, we still get a value of minus 0.3. So even Osnabrück West contains a good amount of information on our quantity of interest. So in summary, these blue bars quantify the degree of dynamic space covariation between OSNAP and our quantity of interest. And in contrast to statistical correlations, we can underpin these bars with dynamical drivers and mechanisms. And we also know exactly what kind of information we're missing. So on my last slide, let me explain how all this, what I've shown you, how this links to its underlying mathematical framework, Hessian uncertainty quantification. The Hessian matrix quantifies uncertainty in our underlying data assimilation framework, our ocean state estimate. So Hessian uncertainty quantification seeks to design an observing system that minimizes the uncertainty in our quantity of interest. And the higher or the stronger the pattern correlation between sensitivity maps of an observation and our quantity of interest is, the more effective is the reduction in QI uncertainty via dynamic space covariation. So Hessian uncertainty quantification really formalizes this concept that I've shown you on the last few slides. And it's called Hessian uncertainty quantification because this sensitivity map essentially forms a Hessian singular vector. So the mathematical framework now applies this concept many times for multiple observations to systematically extract independent sensitivity information from distinct observations and kind of fills the gaps that an individual observation leaves open. So finally, I'd like to emphasize that this method does not require actual measurement values, neither observed nor simulated by a nature run. So what I've shown you is really, actually the only thing that it uses is sensitivity information and dynamic space covariation diagnosed from the equations of motion in an ocean model. So what I've shown you here is really a model-based method to support observing system design before putting the instruments in the water. Okay, so if you're interested in reading more about this, here's the link to a submitted paper, which is available as a preprint. Thanks.
Thanks, Nora. That was great. And as a former program officer, if you could tell me the best place to put something before you actually spent any money, I'd be all on board with that. So I actually really like that, the presentation. All right, so we've had 5 presentations. We have 60 people online. I don't even pretend to know how to manage this. You can actually raise your hand. If you hover over the participants and your name, and you can raise your hand. We can do that if it gets unruly. But I would just suggest at this point that if people want to ask questions, they just ask questions, and then we'll see how it goes. And if you're not being heard, either be rude or just raise your hand, and I'll call on you. So if that sounds okay, then we can start. In other words, just jump in.
Yeah, okay, this is John Toole. I have a couple questions about the Barents Sea study. The first one, you referred to CTDs and other subsurface observations. What do you call other, since Argo floats are CTDs and seals with CTDs on their heads are CTDs? So what other subsurface information are you talking about?
Yeah, so my categories are based on the sort of categories used in the World Ocean Database. So CTDs really refers to ship-based CTDs, and then Argo is of course it's a CTD sensor, but it's PFL data type, profiling float data type, and then similarly there's a different category for drifting buoys, seal data, XBTs, etc. So I really mean CTD in the World Ocean Database. Yeah, so ship-based.
So yeah, so 6 1 half dozen the other, apples and oranges. I mean. So the other question is, NASA now has this call to think about sea surface salinity at high latitudes. Have you thought at all about if there's any information, predictive capability in sea surface salinity?
I think there certainly is. I think for this specific Barents Sea problem, I don't know if it actually matters that much, just in the sense that it's a fairly simple physical system where in the winter, the mixed layers basically extend down to the seafloor. Which is the main reason we were able to get fairly good predictions just using the surface data SST constraint alone, basically. I do think for areas in the Central Arctic that are controlled by a stronger halicline, I think salinity observations could be really important, predicting melt season timing, freeze up timing, those kind of things.
Yeah, except the correlation between sea surface salinity and the halicline depth are strength of the halicline is not straightforward.
That's true. And the halicline in models has been, in my opinion, extremely understudied and just is not very well understood. So I think our models even up to the task, I think is still kind of an open question at this point.
While we're on the Barents Sea, are there any more questions about the Barents Sea? Just for continuity purposes and try to keep it simple. I do have one. That map you showed of CTDs in the Barents Sea showed it pretty saturated, which isn't surprising given all the work, different nationalities working in the Barents Sea. Would it be possible to predict where best you would take CTDs? I mean, are there a subset of those CTDs? Would you take them on the inflow Atlantic current? Would you take them on either side of the polar front? I mean, is there any way to sort of figure out which observations would be more useful?
Yes, so the key predictor, I think, is basically the ocean heat content of the Atlantic water portion of the Barents Sea. So my feeling is a fairly small number of measurements in the Atlantic water portion of the sea would be sufficient, as long as you're past the Barents Sea opening. And then, as CC was mentioning, the Ensemble Kalman filter has a nice localization feature where a given point observation can extend to a much broader spatial radius. So I suspect that a fairly small number of CTD casts would probably get you there.
Great, so maybe just the Kola transect, which runs across that, might be sufficient.
Yeah. So I haven't tried cutting down the CTD observations, but that would be an interesting extension of what I did. Yeah.
Any more questions? I mean, we can come back to the Barents Sea, but are there any more questions to follow up on that or anything that John said? Any other
question in the chat?
Yeah, go ahead.
The question in the chat asks, how important is the Norwegian coastal current?
So I think it's very important in that it's that current that transports a lot of the heat up into the Barents Sea. One interesting thing that kind of came out of our study, actually, the slightly unexpected result that surface data alone was enough to give you fairly good prediction skill. We dug into the mechanisms that were kind of governing the ocean heat content evolution in the Barents Sea. And we found that actually it was mostly the atmosphere that was really driving the subsurface variations, which actually disagrees with some of the published literature, which argues that it's ocean heat transport through the Barents Sea opening that drives the ocean heat content. We actually found the opposite, that there's anomalous positive surface heat fluxes, so fluxes from the atmosphere to the ocean preceding a given summer with a positive ocean heat content anomaly, which is the exact opposite sign of what you'd expect if the ocean was driving it via ocean heat transport. So I think the ocean's important in the sense of passively advecting heat content anomalies, but it's not really, the dynamics are actually not that important, is what we found.
Other questions? On other topics, other presentations?
This is.
Oh, go ahead.
Sorry, no, I wait.
I don't even know who that was, but go ahead.
Well, it was Igor, and I have a question to Cecilia. Well, Patrick Shapiro explained clearly the difference between two approaches, and Cecilia classified her study as OCCE, but at the same time, a significant part is devoted to assimilation. So I just try to understand, maybe it's very simple, but why OCCE example, as she described, take into consideration a lot of assimilation? And what was the bias that significantly improves results?
I think well, let me know if I don't answer your question correctly, but I probably don't use the term OSSI the same way that Patrick does. I was adding the extra S because it was purely simulation based, that I was simulating synthetic observations. So other than that, that's the best explanation I can give, that it's an observing system, purely simulation experiment. The reduction in bias that we performed with just statistics was in the extent of the sea ice. So we were able to quantify where the model consistently put sea ice in the wrong place or had a lack of sea ice systematically as a function of lead time. So the errors grow with lead time. So you can actually quantify the error as a function of lead time and then correct it. The reason I wouldn't advocate for doing that instead of improving models is it only corrects one variable. It only corrected sea ice extent, which is great if that's what you care about. But if you're interested in a full coupled system where feedbacks are involved, it doesn't cut it. But it proves that we could do better. So
okay, and bias was estimated for all years included in simulations, yes? Not climatic bias.
Well, it would be biased in just say because the model has incorrect winds and incorrect currents in the ocean, incorrect heat transport. That those, but they were systematic, so that it would give rise to systematic errors in the sea ice. And yes, if you computed the climatology in the model and compared it to the climatology and observations, they would differ.
Okay, thank you.
Mm-hmm.
Okay, we've got a question on chat from Jackie Richter-Mengi, who apparently is bashful today, doesn't want to ask it, so I'll ask it for her. And this is to anyone, presenters or otherwise. Are model results currently being used to influence the design of the Arctic Observing Network, or more generally, examples of models being used to influence the deployment of observational platforms? Anybody want to take that?
Well, this is Patrick. I mean, I can try. I'm not fully aware of models being involved in the design of AON. I think there are some emerging efforts really now beginning to take that seriously. The more generic question is whether deployment of the observational platform is, whether that's informed by models. There is a rich literature in the atmospheric community, right? And so at the end of my talk, that I didn't show, but at the end I've provided sort of a list of papers, and actually many of these concepts have been established and well developed in the atmospheric community. THORPEX is a very famous experiment in the North Atlantic where this has been going on for many years. And so the answer is yes, it's being done in that community, but I am not aware that it's being done right now in the Arctic. But I might be missing some ongoing or already published studies here.
I would just point out that it's a lot easier to put a buoy or a moored array into a computer than it is into the real Arctic Ocean.
Yeah, no, that's perfectly true.
So
I think yeah.
You have to put that constraint on your Aussie, right?
Right.
Can you actually do this measurement?
Yeah. So that's why I mentioned at the beginning, I think nobody here advocates that this is sort of you have to follow the model by the letter, if that's what you say. But I see it as sort of, it's a tool, it's a quantitative tool. You have a toolbox, right, of many, number of tools that you are in trying to inform and guide how you design your observing system, right? And so some of them are purely practically driven, right? So this is where we can go, this is where we cannot go. Actually, some of this can actually be even formalized with a penalty function in your quantity of interest. But beyond that, it's if you accept that their model has certain things that are robust, and I think some things have been shown here where there is some mechanisms that I think people generally agree that these are at play, then these model tools really help you to tease them out and actually to provide this information. And then of course you have to weight it, upweight or downweight it with some other practicalities if they're not built into your design system, right? I mean, if you're a glaciologist and the model tells you to put your GPS sensor somewhere, and then you figure out it's a heavily crevasse glacier field, then do it. So I agree. The other point I was going to make is that some of these tools are sort of fairly sophisticated, and we're also, while we apply them, right, so to real observing system design, we're also still learning how to use them well, right? So how to fully develop them, how to make them efficient, and how to interpret them. Again, if you draw from the numerical weather prediction community, that of course has been a long and entangled process, and some people here on the call can actually speak to that. This goes back to the 1990s, the late 1990s, with applying such methods, and they are today like forecast observation, forecast sensitivity observation impacts. They are integral parts of any forecasting system in the atmosphere, right? But I think, so what I'm saying is we are also still learning, right? So how to use these tools that are sometimes computationally very involved. So it's actually not that easy to just put the buoy in the model. So it's actually not as easy as that.
I might suggest something. Patrick, and assimilating modelers, you have something you call the cost function. But what John is saying is that there's a actual cost function for putting things in the water. And I mean, really not joking. I mean, why not? You could work modelers with somebody like John to figure out what that cost function is and try to minimize that as well.
Yep, absolutely. I agree.
Back to that question earlier, that there are a couple of examples where we've been asked to provide information about where to put observing field stations, for the Navy, as well as NOAA flight track paths through the Arctic by looking at predictions of sea ice. So there are examples where they weren't specific instruments. They were, where to start a station or something like that.
One other point I'd like to add, if CC's done, is I think it's also important to, it's exciting to build new networks, of course, but I think we do have a lot of great data already. Limited, but there is a lot of data out there. And I think one possible role for modelers is actually to use the data we do have and kind of demonstrate its value. And therefore provide some motivation for, funding agencies and nations and whatnot to sustain these observing programs that have been going on for a while. And I think that's something really critical to keep in mind, is that it's not just about having snapshot data that's dense, but having time series data is so critical, especially for prediction type applications. So I would just like to throw that in as a flip side, where maybe the modelers can help out the observationalists a bit as well here.
Actually, I would disagree that we have a little bit of data. We are swimming in data. We are, we are drowning in data. This isn't to take away from people who are still collecting data, but I would argue that we are underutilizing the data that we currently have. And there are some systemic reasons for that, dating back to the Arctic Observing Network program design, actually. But we are, in my opinion, but there are certain areas where we don't have enough data, but we are overwhelmed with the amount of data, and I would argue that it's being underutilized. Okay, with that rant, is there anybody else who wants to weigh in on that question? Are there other questions? We've got about 15 minutes or more here.
I think I'd like to throw a broad one out there as well, kind of queuing off Jackie's question. One of the reasons why the co-chairs were motivated to convene this discussion is because we felt like this community of practice needed some fostering. And in particular, it seemed that it was a pretty small community in the Arctic working on these types of efforts, and that there could be more room for a tighter and more deliberate collaboration between observationalists and modelers active in this area. What do you think are the opportunities or what's standing in the way from increasing that interaction, and how what do agencies need to hear about this? Are program calls too limited? Are people just not connecting because they're in different rooms at meetings? What are some of the things that could stimulate more productivity here?
I can stick my head out again, but or maybe somebody else.
Yeah, go ahead.
I think that the most valuable way to do this productively would be in tight collaboration between the modelers and the data assimilation people and the observationalists, because it teaches all of the communities of the merits, but also of the shortcomings of each, right? So we as modelers, we're aware of our limitations of the models, and same with observationalists, and having just a tight, collaboration is actually at the individual level is actually really a good way to learn from each other. And that I think from a programmatic perspective, what's been somewhat difficult is that when the idea of observation systems come up, right? Oftentimes, I'm going to simplify this a bit. Let's do the observation first, and then we'll do the modeling, right? And that what I've been trying to advocate, and I think what you see out of these talks, right? So they're all involved, right? They take a bit of time to design well, to conduct these observing system experiments well, to actually understand them. In some cases, even to develop them then to a level of maturity. Some of these are computationally very, very involved methods there, where even computational science and engineering is still involved in developing these methods, making them efficient, making them scalable to real systems. And so while we are deploying them to real world problems, we're also still developing the tools and methods by themselves. And so I think there has to be some recognition that there's some science also in how to do this well. And there is some time that needs to be spent to do it that oftentimes isn't available because the observing system has to be deployed maybe in a year or so, and that can be difficult. So that's sort of one perspective of what's limited this. But I have the impression, as I said, right, that really people are taking this on board more and more.
Can I ask a question?
Yeah.
What is there an example out there of what you're proposing, or specifically, there was some Aussie activity, and the Aussie-ish people worked with the observationalist people, and it guided an observational program. Is there a good example of that?
Yeah, so I can give examples from the subpolar North Atlantic. So there was what the OSNAP array was to some extent designed by what we called an Aussie type experiment, right? So OSSE type. So the paper by Feli Lee and Lozier and others, 2017, basically sampled from a high resolution ocean model, right? And looked at how, the synthetic or hypothetic placements, how good they were to reconstruct, transport across these OSNAP sections. That would be an Aussie type. And some of the things that Nora Loose now is engaged with, and also Helen Piller here, is to actually revisit, these issues and see whether the sampling can be made more efficient, for example, right? And so these are examples from quickly that come to mind for the subpolar and the North Atlantic.
Yeah, I just wanted to add that the study that I presented, it was actually originally started with Craig Lee approaching us and NSF as well for trying to quantify first what the optimal information you can obtain and what kind of error you expect before one can deploy the Argo floats in the Arctic. So we're still in the very early phase, but I would say that was an example already at the beginning that Craig Lee and his team recognized that instead of just deploying that, they would like to understand more, and they understand that we have the tool, and that's why the whole process got rolling because of that. So.
Yeah, and I was just going to make that point, and then I was going to ask, now that you've nicely demonstrated that the deeper floats give you fairly reliable data, certainly more than the surface floats, is there a plan now to follow up on the next step and to think about deploying the deeper floats?
I think that was the plan, but we are trying to, we're trying to follow through because there are all kinds of delays as usual. As you can see, this project was funded in 2014, I think, or 15, and it takes now 2020 before we finally get the publication, at least in revision. So it is a slow process, but we are trying to see whether we can make the next step.
Good science takes time on. It'll be fine. So are there any other questions on that or any of the other presentations or topics? Betsy, did you have one? No, you were fiddling. All right. Yep. Anybody else? Yeah, Mitch.
I had a question for Nora actually on her talk. I thought it was really interesting. And just regarding these like dynamics-based covariances that you were mentioning, are those built by hand based on some sort of physical intuition that you, the scientist, has to have somehow? Or is the process automated where there's an algorithm that's kind of finding the relevant dynamics-based covariances?
They're teased out by the Hadron model. So the Hadron, you remember I showed 2 sensitivity maps. So the sensitivity of the Arctic Ocean heat content and sensitivity of OSNAP heat transport. So if you have one quantity of interest, the Hadron model, running the Hadron model, you can think about it as running a model backwards. So it gives you all the sensitivity regions, like where in the past an atmospheric forcing could have led to a change that we're seeing now. So this is what the Hadron model does. In some sense, it runs backwards. So it gives you all sensitivity regions. I only showed sensitivities to wind, but it also gives you sensitivity to air, sea, heat fluxes, and initial conditions, temperature, salinity. So, and then by basically what I showed, kind of by finding the overlapping sensitivities, this gives you the covariance doing this pattern correlation. So yeah, to answer your question, it is automated. It is basically given to you by the Hadron model.
May I add something about the Hadron model? The Hadron model is based on most likely the tangent linear, that is a linear approximation of the nonlinear model. So if we are looking at an improvement in the nonlinear part of the model, or some assimilation of data that will provide some information in the nonlinear part of the model, which is usually the case when we want to look at the variance and not the mean. Therefore, how to avoid those problems of the nonlinearities that suddenly disappear in the data assimilation.
So yeah, you're making a good point. So there are pros and cons with every method, right? And this is actually, yeah, this is a limitation of the Hadron method. So that, right, as you're saying, it is based on, it's kind of a linearization around the nonlinear model dynamics. And if the model is very nonlinear in some regions, then this approximation might break down. So we always have to check if how we're doing. But then the big advantage compared to ensemble-based methods, for example, is that we're actually following, while we're following the model dynamics, right? We're not breaking the physics, because some of the ensemble approach, you run your ensembles and then you take the mean, and the spread is basically, yeah. So that doesn't follow the full model dynamics either. So there are always some disadvantages and advantages with each method, and so I think that's why it's really important what other people have said before. It's the most, we will benefit the most if we all work together. yeah, observationist modelers, and even like between the different model-based methods. I think you can learn a lot by comparing these, and yeah.
Yeah, it's what I was gonna recommend for our Aussies is to do, or different Aussies, is to actually get several modeler and techniques to assess the where to put the instrument, because each and every technique will give different answer, and in some places they might very much diverge among the data assimilation techniques. Even between a Kalman filter and an Ensemble Kalman filter, there will be some differences.
I would argue that would be a great proposal to NSF to put together a group of people who could have that discussion in a workshop.
Sorry, I'm having trouble with the connection.
So
please try again in a moment.
Someone's talking to me. Anyhow, but that's neither here nor there since I'm not at NSF anymore. I'm just a suggestion that I think there's a lot more work that can be done if these groups, work together, which is usually the case. Any other comments, questions? I think we should have combined meetings more often. This has been, I find particularly interesting. We've got just a couple minutes left, and I would ask people that if they found this interesting and have some, other ideas for these type of joint presentations or other topics you'd like to follow up on, please let one of us know. We've got just a couple of minutes left. Then, are there any? And at this point, we typically ask anybody if there are any updates or announcements, ideas for collaboration, etc., from IARPC. That's one of our jobs. And we rarely do it, so now I'm taking 2 minutes to do it. Anybody want to announce anything of excitement? Okay, yeah, that's pretty much how I feel too. All right, any other closing comments? I would thank all the presenters. Those were really interesting presentations. They were spot on for what we wanted to do, and they were also spot on time. Francois, do you have a question? Or did you hit your hand? Oh, you were clapping. I don't know what those things,
just clapping.
Yeah, I don't know what those things mean, so they completely lost on me. All right. But anyhow, I thank all the presenters. I know it takes so much time to put those together, so I really want to thank you for that time and for sharing it with us. Any other comments? Any other comments from Sandy, Sally?
Just adding my thanks. I think this really delivered on what we were trying to accomplish, at least as an initial kind of learning discussion. And second Will's point about please follow up about how we can build on this topic.
Okay. All right. With that, then it's nice to see so many familiar faces and some new faces. So please don't be a stranger to this space. You will certainly be getting emails, and if it interests you, please join us. So with that, I wish everybody a good afternoon, evening, or morning, depending on where you are. Okay. Thanks a lot.
Thanks, everybody.
Yeah,
Thanks,
thank you.